you could completely skip the passage. You could just look at the question and you know it's A or B from this.
Phil back with another MCAT podcast after getting destroyed last week with our Chem Phys passage. Hopefully this week's a little bit easier.
Well, it kind of depends. Are you a chemistry person or are you a physics person?
I'm a podcast person.
Yeah, podcaster. Yeah. Well, the previous passages are pretty difficult chemistry passage. This one is going more in the physics realm.
Okay.
I don't know if it's like necessarily easier, more difficult. There's certain students who are going to think 9 is easier than 10 and vice versa. Yep. I think it kind of comes down to individual strengths.
Well, I love physics. I also loved chemistry, but I was one of those rare breeds. I just didn't like biology, which is funny because I love anatomy. But anyway.
Yeah. No, I'm totally with you. Give me an equation or a rule that I can apply to 10,000 scenarios. Don't make me memorize a list of things.
Exactly.
And I feel like that's what biology is a lot.
Exactly. All right. Well, if you want to follow along and see what we're seeing, read what we're reading, go to our YouTube channel, premed.tv. We have videos of all of these from full length 1 posted as we release them.
Yeah, this is our last passage from the Chem Phys section.
Thank the Lord. All right.
All right, so hopping in here, if vesicles are deformed while being transported through the body, vesicle membranes exhibit a tank-treading motion. During movement, a force capable of lifting these non-spherical buoyant vesicles away from the substrate may result. To understand the role of vesicles may have in heart disease, researchers designed synthetic lipid vesicles to mimic erythrocytes and subjected them to shear flow close to a vessel wall. The aim was to study the effect of vesicle buoyancy, size, and volume. Kind of an interesting thing here. They're basically like taking these like bubbles and like slamming them into the wall and see what they do. Evidently, they're doing this tank treading motion, which in my mind like makes me think of like tumbleweeds, kind of like rolling along. And they say that this can lead to some buoyance going through this. So once again, they're kind of giving us some background info. Not a lot of really highly testable stuff. They do mention erythrocytes, so maybe there'll be some questions about red blood cells. But I'm probably not going to need to come back to this paragraph to answer any questions. Yeah. So the unilamellar vesicles are prepared by electroformation, 1,2-diloyl SN-glycero-3-phosphocholine, which I don't ever want to say again, was dissolved in chloroform methanol solution. The solution was then spread on a conductive faces of 2 glass plates coated with transparent indium tin oxide, EDO. The plates were connected to a 10 hertz alternating current, and the resulting 1.5 volt potential difference was maintained between the plates for 3 hours. Lots of numbers they're giving us here, like 10 hertz, 1.5 volts, like 3 hours. Definitely can expect to maybe see some questions.
Yep.
Concentrations of solutions were altered to cause density variations. Finally, vesicles were diluted in a glucose solution of higher osmolality but lower buoyancy. Osmosis produced partially deflated, flaccid, deformable objects. Vesicles settled on the substrate and their buoyancy was controlled and varied. Figure 1 shows partial results and data for selected vesicles. So basically they created these vesicles trying to mimic red blood cells, and then they put them in like hypertonic solution, so it pulled some of the water out. They became kind of like flat tires, if you will. And they want to see how these are going to act under these scenarios.
Yeah.
They give us figure 1.
Figure 1.
Which the actual...
Looks very similar to the UFO videos that were recently released.
Right, I think Bigfoot's somewhere in there. Like there's not a lot of stuff coming from that first paragraph that first figure. I'm like, I mean, what would I do to calculate something or like interpret something? Yeah. However, the explanation gives us the shape diagram of vesicles under flow of one vesicle for different flow rates. So we have different rates of like the movement of like blood flow that we have going on here. And we can see that under condition 1, it seems like it's stuck to the plate. And so you can kind of see the reflection there. But then as the flow rate increases, we have like it starts to kind of detach. And so we see the buoyancy here by increasing the rate of flow within this. Okay. So the deflated vesicles detach and lift off from the substrate when the wall shear rate is higher than a minimum value, GC. This minimum depends upon the viscosity, the density of the vesicles in solution, the vesicle radius, and the vesicle radius. When the vesicles are unbound from the substrate, they hover at a distance d from the wall, which increases upon increasing the shear rate. At a d value sufficient to establish equilibrium, there is a hydrodynamic lift force, which is equal to the apparent weight of the vesicle. And so there's a lot of stuff going on here. They give us this equation to calculate the apparent weight based upon like density and all of these other things. Expect to maybe see something like doing a calculation. But as I look at this, like there's that radius to the third and there's like DRG. This seems like kind of a complex math problem. So they're probably more likely to test relationships. Whereas I've noticed that like if I increase the radius, that's going to increase the apparent weight. Actually all of the variables, if you increase them, it's going to increase your apparent weight. With the exception of like the radius is to the third power. So that's going to be an exponential increase as we go through there. But yeah, it seems like that's just kind of like setting us up to look at table 1 where they give us some actual things. I will say before I jump too far into this, they kind of are telling you that they're looking at buoyancy, like some buoyant forces. That's where apparent weight comes in. Apparent weight is how much does something weigh when it's underwater, right? I'm not going to say how much I weigh, but when I'm in water, I weigh less. And so that my apparent weight is how much I would weigh if I was completely submerged in water. So we have this table 1 where they give us all of these different values. My N naught, which I'm guessing is like, different experiment numbers. We have my radius. We have my P, which is apparent weight. We have my DRG, which is in pascals per meter. We have the viscosity of this thing divided by the viscosity of water. That's the funky N that we have there. 1 minus, I'm guessing, the velocity here. We have GC, which from up above is the shear. What do they call this? The shear something. Where's the GC? I know it's somewhere up here.
Shear something.
Yeah. Misplaced it. Anyway, it's something up
that
here.
Deflated vesicles detach and lift off from the substrate when the wall shear rate is higher than a minimum value.
Yeah, so that's the minimum value for the wall shear rate.
Yep.
And then we have the angle that we have here. And it seems like they only gave us that for some of these and not for all of them. Yep. So they might maybe ask us a question about this. And then as I look for the explanation of the table, it clarifies some of those things. So V is the reduced volume, and over N is the viscosity relative to water, and the angle is the angle of inertia relative to the flow direction. And so how these things are moving relative to the flow itself. So kind of a physics passage, a little bit, fluid dynamics, some buoyancy stuff going on, some viscosity things. But as is always the case, the MCAT gives it kind of a bio spin by looking at the erythrocytes and like stuff in blood vessels.
Yeah.
So looking at the first question here, question 53, what is the lift force for the vesicle reported in table 1 that would be the last to detach from the vascular wall? And then we have 0.2 piconewtons, 153 piconewtons, 68.7 pascals per meter, and 121.9 pascals per meter.
What is the lift force for the vesicle reported in table 1 that would be the last to detach from the vascular wall? So the last to detach from the vascular wall, I'm assuming is going to be the weight, the one that's heaviest. Just seems to make sense. So which one's the heaviest? We have this P value, the apparent weight. So the biggest apparent weight one is this last one. So just thinking through that. Okay. So what is the lift force for the vesicle reported in table 1 that would be the last to detach from the vascular wall? I think it'd be too easy to go, it's 153.6, which is the apparent weight, because that's what that is, and it's in pascals per newton. Pascals newton.
That's a piconewton.
Piconewton.
Like a millimeter sort of thing, like our millinewton.
I'm assuming it's going to be too easy to just pick that number because it matches. So I'm not going to. DRG, we said is... Oh, what did we say DRG is? And this is
that's a mixture of a lot of things, right? D is the distance, R is the vesicle radius, G is, I think, just like 9.8 meters per second squared.
So that's not a specific thing. Oh man, so it's weird. It's like because 121.9, which is the answer choice D, is also the DRG for that last one.
So it isn't just asking like which of these would be the last. It's asking what would be the lift force.
Correct.
And so a lot of students, I would encourage them to hang on, like pay attention to units, right? We're looking for a force, which is measured in newtons.
Yep.
And so like a Pascal, which is what C and D are in, those aren't newtons. A Pascal is like a Newton per meter squared. And so C and D are both going to end up being like newtons per meter cubed. So that's like a force divided by a volume, which is not a force. So even if you have like no idea what's going on, if you know that like a force is a Newton, then the answer's got to be A or B, which feels good. Like to have like you could be completely lost and you're at a 50-50 on this.
Yep.
You could completely skip the passage. You could just look at the question and you know it's A or B from this.
Okay.
Which feels good. I could feel your self-doubt. I'm wondering if that happened like after the chemistry passage from the previous one. You're like it can't be this easy. I don't trust it.
Yeah.
But it is actually going to be B for this one.
Yeah.
Just
okay. It is that easy.
153. Yeah, it's the apparent weight, so that's how much it's going to weigh to lift it, and so that one's going to require 153 newtons to lift, and A is going to require just 0.2 newtons, so that one's going to be a whole lot easier to lift, and it's going to come off the wall easier.
So let me ask you, so 153.6 piconewtons, to me, that's the force that would just keep it there, but to lift it up, it would have to be more than that.
Yeah, it would have to be more than that. Yep, absolutely. So
the answer should be 153.7.
Yeah, right. So that would be the 153.600000001.
Yep.
Right. Yeah.
Okay. Oh, all right. So it was that easy. All right. So an easy one just from and that's always that trick, right? Of just really understanding and paying attention to the units and helping your answer choices with that.
Yeah, I love units. There are a lot of questions out there, and I feel like if anything, the AAMC has more questions that are answerable that way than we do. Because we want to really encourage students to know the equations, because sometimes you have to know the equation in order to get it right. But the AAMC, a lot of times you can use your units, and so sometimes that'll just straight up give you the answer. Sometimes it gets you to a 50-50, which is still really nice.
Yeah.
But sometimes you don't even have to do anything beyond that, just because like the answer's got to be in newtons because they're asking for a force.
Yeah. Okay, question 54. According to the results presented by the experiment, the relationship between the lift force and the vesicle radius would be best described as, all right, A linear, B inverse, C exponential, or D sigmoidal. And so the lift force we know from the last question is kind of equal to that P, the apparent weight.
Right.
And so we know the equation for P, for the apparent weight, because they gave it to us. This for whatever that P is, radius cubed divided by 3, then times DRG. So radius here, because it's cubed, that there is that exponential relationship. So the relationship between the lift force and the vesicle radius would be described as exponential, I think.
Yeah. So just looking straight at the equation, absolutely. I mean, like if radius doubles, the apparent weight is going to be 8 times bigger because it's raised to the 3rd power.
Yeah.
Now you can answer it that way by looking at the equation. You could also just look at the table, right? As we go from like the first row to, I'm going to say the 4th row, because the radius there goes from 8.7 to 27.3, which is about 3 times bigger. Because 9 times 3 is 27, which is close enough. Now, the apparent weight goes from 0.2 to 13. That is not 3 times bigger.
Yep.
That would be if it went from like 0.2 to 0.6. And so this is like way bigger. So it's definitely an exponential relationship going through here. It would be inverse if it was the opposite. If one doubled and the other one doubled, that would be linear. Sigmoidal would imply that it's increasing slowly at first and then increasing very quickly and then increasing slowly again. And if we look at this table, like it seems like the apparent weight just keeps increasing a lot. It never seems kind of like level out here.
Yeah.
But that's how you can answer it using the table. Honestly, it's probably easier to do it the way you did, but just look at the equation. Like that's an exponential equation, exponential relationship.
Alrighty.
All right. So question 55, when the researchers connected the solution-filled glass plates to the flow chamber of the AC generator, alternating current generator, the indium tin oxide coated plates most likely functioned as A, a resistor, B, a capacitor, C, a galvanic cell, and D, an electrolytic cell.
Solution-filled glass plates of the flow chamber to the AC generator. ITO coated plates functioned as. And so just for my own thing, that indium tin oxide, resulting 1.5 volt potential difference between the two plates. A resistor and capacitor just don't make sense for this question. I don't know. So I'm gonna go 50-50 with C or D and choose D, but I don't know why.
Yeah. So going through a resistor is something that's we're going to have trouble getting like current through.
Yep.
But current will go through it.
Yep.
A capacitor ends up like building up charge on 2 different areas. A galvanic cell is a battery that is releasing energy, and an electrolytic cell is a battery that we are inputting energy into, so like recharging. So as they go through this, we talk about these plates. And there's a potential difference between them, 1.5 volts. So that means that there is a difference in charge from one plate to the other. And we're creating an electric field or a voltage here. So it's actually just going to be a capacitor. As a matter of fact, there's a type of capacitor called a parallel plate capacitor, which is exactly what this is, as we have the 2 glass plates and some distance separated between them. Now, very often I would say that there's got to be some form of like power source here, and the power source could be a galvanic cell. But the passage tells us that we connect this to this alternating current, like outside of this. And so electrochemical cells tend to produce direct currents, not alternating currents. So it makes me kind of want to lean away from the electrochemical cells, the galvanic or the electrolytic. Definitely kind of this question is not so much a like pure passage. This is like an outside knowledge thing of like circuits.
Yeah.
So once again, another example of how the MCAT likes to smash multiple topics together. This is a passage mostly about fluid dynamics, but now all of a sudden there's a question in here about circuits.
Yeah. Thanks, MCAT.
Yeah. So last question from our last passage in Chem Phys.
I will miss you.
So, according to the experimental procedure, which of the following describes the physical properties of indium tin oxide? 1, opaque. 2, electrically conducting. 3, solid at standard temperature. Now, we have like a bunch of different answers here with Roman numerals. So, A is just 2. 3. B is just 3. C is 1 and 3. And D is 2 and 3.
So, it doesn't make sense that electrically conducting wouldn't be a property because we just talked about all the electrical current and stuff happening on this. So 2 seems like it has to be an answer. So that would throw out B, which is 3 only, and C, which is 1 and 3 only. And so the question is it only electrically conducting, which is A, or is it electrically conducting and solid at standard temperature? The thing for me, I don't remember seeing anything about temperature in the passage, about is it heated, is it cooled, etc. All I see is that this ITO was spread on the faces, which tells me that it's probably not solid.
Well, it's spread on these plates, and then we're running water through in between the plates to kind of like see how well the vesicles kind of like lift off of that.
Yeah. So you're saying it is solid?
Yeah, it's probably going to be a solid, because if it was a liquid, it would probably just wash away. And so we're coating this with something here. Another thing to note is that we're dealing with a tin oxide, which is going to be a metal, right? It's an oxidized metal, but it's still a metal. It's going to be like a nail that's rusted.
Yeah, and mercury is only like the random metal that's liquid.
Mercury is the weird oddball one. And so given the fact that this is just some like metallic oxide, it definitely makes sense for it to be electrically conducting and probably a solid.
Okay.
Note that they say in the sentence where they bring that up, it's like transparent indium tin oxide, which means it's not going to be opaque.
It's not opaque, yes.
Because it's transparent. Like it literally says transparent. So you can eliminate Roman numeral 1 from that pretty quickly.
Yeah.
Yeah. And so that's it. That's it for the passage. A lot of stuff going on. Once again, they gave us a lot of data. You know, that previous passage had a lot of data in a table. This one also has a lot of data in the table. You didn't end up using quite as much of it, though. Focusing specifically in on the topics that the MCAT tends to care about. You know, given this passage is about like buoyancy, like the apparent weight, how much it weighs in water seems to be like the main thing they really cared about from this passage.